Okay, so let's look at a specific case of a sampling distribution. So there are sampling distributions for a lot of different statistics, but we're interested in the one for this sample mean. Remember, we call this sample mean X bar. So suppose that we have a simple random sample of size n. So we have n subjects in our sample, and we know that the population that we drew that sample from has a mean of mu and a standard deviation of sigma. Then our sampling distribution for X bar is also going to have a mean of mu, but the standard deviation is going to be slightly different. It's going to be sigma divided by the square root of n. Okay, so we're going to take a look about some of those facts. We'll come back and revisit the bottom half of this slide in a little bit, but let's take a look about some of those facts. So the mean of X bar is going to be equal to the mean of our population mu. So what we say is that X bar is an unbiased estimator of our parameter mu. So in other words, X bar is sometimes a little bit above mu and sometimes a little bit below mu, but it's not consistently always an overestimate or always an underestimate. It varies back and forth. And so there isn't really a bias there, so we call it an unbiased estimator. Okay. Now our standard deviation, you'll notice that we're now dividing our standard deviation by the square root of n. And that's because if we look at a bunch of averages, those averages are going to be kind of closer together than a bunch of individual observations. Individual observations can have a lot of outliers, and so they'll be further spread out. Whereas an average, kind of those outliers get pulled more towards the center because they're wrapped into that average. And in fact, the bigger your sample size is, those averages are actually going to become more tightly packed together. Okay, so let's take a look at our classwork. We have this one called Measurements in the Lab. Let's put this into practice and see if we can make some sense of these ideas. Okay, so Juan makes a measurement in a chemistry lab and records the result in his lab report. Suppose that if Juan makes this measurement repeatedly, the standard deviation of his measurements will be sigma equal to 10 milligrams. Juan repeats the measurement 4 times and records the mean X bar of his 4 measurements. All right, so we have a couple of questions here, so I'm going to pull up the classwork and we can work on that. Okay, so Juan repeats the measurement 4 times. So what is the standard deviation of Juan's mean result? Okay, so we know that the standard deviation formula is sigma over the square root of n. So sigma was given to us to be 10, and he's doing 4 measurements. So we're going to divide by the square root of 4. So it gives me 10 divided by 2, which is 5. Okay, so that's the standard deviation for all of his X bar values. Question 2 says, how many times must Juan repeat the measurement to get to a standard deviation of X bar for 2? So in other words, what we want is sigma over the square root of n to be equal to 2. Okay, so we know that sigma is 10, so we need 10 over the square root of n to be equal to 2. So what I'll do is I'll multiply that square root of n up here, and I'll divide the 2 back. So I have 10 over 2 is equal to the square root of n, which means 5 is equal to the square root of n. If I square both sides, I get n is equal to 25. So we would need a sample size of 25 to get our standard deviation down to 2. Then the third part says, explain to someone who knows no statistics the advantage of reporting the average of several measurements rather than the result of a single measurement. Okay, so the problem with reporting a single measurement is that sometimes a single measurement can be an outlier. And you have no way of knowing that unless you repeat your measurements several times. And really the best is to get an average of those measurements, okay? So that is going to give you the closest idea to what your true population mean